about symmetric tensor networks.
Thank you. Yeah, I would like to thank the organizer for putting together this very nice workshop and giving me this opportunity to present some work. So I'll talk about the symmetric tensor network and topological phases. I think Zheng Cheng already gave a very good introduction about topological phases. But let me firstly thank my collaborators. So my student Shihan Jiang is really the driving force behind all these works. And we also collaborate with Professor Junhong Han's group at SKKU, and Braden, Chaoming, and Michael at the Station Q. Zheng Cheng already mentioned this, but let me mention this again. So I want to mention there are two types of symmetric topological phases. So this talk will be about symmetric topological phases. So the key word is both is symmetry and topology. So it turns out that there are two kinds of symmetric topological phases. One type is so-called SPT phases, which Zheng mentioned a moment ago. So the key feature for this SPT phases involves the following. So in the bulk, expectations are rather trivial, but on the boundary there are some special edge states. So the famous example including this AKLT chain, either quantum Hall, insulator, and Professor Asaki contribute a lot to this spin chain, which I think is the first example of SPT phase. Another type of symmetric topological phase I will talk about is this so-called SET, or symmetry enriched topological phase. So here the difference is the following. So the bulk excitation is non-trivial already. In the bulk, you have something called topological order, which Zheng also mentioned. Essentially, it means in the bulk you have some anyon excitation in two spatial dimensions, and something analogous in three dimension. Not really anyon, but there is gauge charge and gauge flux in three dimensions. Roughly speaking, you can think about this topological order as some kind of gauge theory. There are these quasi-particle excitations which cannot be created by local Hamiltonian. This is basically a local perturbation. So, in this topological order phase, there is this famous phenomena which is interesting, which is called symmetry fermiization. In fact, there are other phenomena, but maybe let me focus on the symmetry fermiization. For example, in a Loftin state, you can have this quasi-particle carry a fractional charge of the global symmetry. So this is directly related to the fact that you cannot create one quasi-particle alone. You always have to create, say, three of them. They may be created in different places, but you cannot create one alone. So in terms of gauge theory, this is something maybe familiar. It's just Gauss's law. It's like you cannot create a gauge charge alone. You have to create, say, a gauge charge and some anti-charge somewhere else. So examples include this Topological, which Zheng mentioned, and some gap quantum spin liquids, and the fractional quantum Hall states. So I will pay attention to these two different types of topological phases. So just maybe keep in mind that this guy has no topological order in the bulk, no anyon in the bulk, but this guy has anyon in the bulk. So that's the difference. And I will study how symmetry interact with the topology. Okay. So I will focus on this bosonic topological phases, which require strong interactions to realize. And in the past, there are a lot, for example, the fermionic topological, in particular, this topological insulator has been realized in experiments. But here, the bosonic system is particularly, at least intellectually interesting because they always require strong interactions to realize. Because for bosons, if you don't have interaction, they just condense. So in this field, there are several different kinds of issues. So let me mention my motivation. So my motivation includes both these more conceptual issues and also these more practical issues. So conceptual issues include this, for example, this classification problem. So we want to have a systematic understanding of, for example, what are the possible types of SPT phases. This problem is particularly unsolved in the presence of spatial symmetry. So previously there are some understanding like case by case, but there's no systematic understanding. But I also have very practical motivations. So theoretically, we know there are a lot of these topological phases. This is bosonic SET or SPT phases. For example, there could be thousands of them. But then if you try to ask yourself, can we realize them in some more or less practical Hamiltonian that may be relevant to some material? Then you'll find almost none of them are realized, except for this, for example, very few examples like this AKLT spin chain or Houghton chain. So you can ask why? Why is it so difficult to find this simple model realization or practical realization of this topological phases? So I would say there may be at least two challenges. So one challenge is we probably need some more physical intuitions or guiding principles. So if you go back to history, you can ask why these topological insulators got realized. So of course there are many reasons, but one of the important reasons is the inventors of these topological insulators. They provide a very simple guiding principle, which is the band inversion picture. It just tells you that if you invert the band, you necessarily get a TI. And this band inversion picture is somehow easy to figure out in this first principle calculation. So that's how this TI got realized. So we need something like that. So we need to have some physical guiding principle. We do something, and then we get this bosonic topological states. But because here we have strong interaction, we don't have band picture, we cannot have band inversion. But the question is, can we have something similar kind of guiding principle? We do something, then we necessarily get the topological states or phase. So another challenge is from the numerical side, because to really pin down the phase diagram, we need to do some numerical simulation generally. And our capability to reliably simulate correlated models are simply very limited. And so in this sense, it's highly desirable to develop new kinds of numerical methods, in particularly suitable for these topological states. So one very concrete question one can ask is, can we write down very generic trial-wave functions for these topological states? Because if you think about how do we numerically simulate correlated models, in the general system, we basically always do very regional simulation, because other numerical methods suffer all different kinds of problems. So namely, we try to find a way to write down generic trial-wave functions for these topological states. So those are the motivations. Okay? And I will go very slowly, and I hope I got questions. Yes, please stop me. So let me present the result. The result is not a particular solution for some particular problem. It's a rather general machinery. So it's based on this tensor network formulation, like matrix product space or perhaps or 3D generalizations. So this machinery does the following job. So it systematically but partially classify topological phases. At the same time, we can construct very generic 12-way functions for almost every phase. So in particular, if your symmetry group is discrete, this construction can be so for every phase you can have a generic wave function. Even for continuous symmetry, sometimes you also can have a construction. So the way that this machinery works is following. So all I need to know is some input. You need to tell me the symmetry of your system. So it includes all kinds of symmetry, including, say, internal symmetry like spin rotation, or some spatial symmetry like space group symmetry. And then there's a well-defined procedure to follow. And at the end of the day, this machinery generates a classification of topological phases, partial classification of topological phases, and the construction for dynamic wave functions. So I will describe how this works. So what this machinery really does is answers the following question. It really tries to classify symmetric tensor network wave functions. So imagine you have this wave function, and imagine you have some symmetry in your system. And you want to write down this tensor network wave function respecting the full symmetry. And then you can ask the following question. So can I smoothly deform this one symmetric tensor network wave function into another symmetric tensor network wave function without breaking symmetry smoothly? If I can smoothly deform one to the other under certain assumption, I will claim they belong to the same class. And if I couldn't, I call them in different class. So this classification is really a classification of symmetric tensor network. And if you think about this question is directly, it basically sounds like a topological question, right? Because by definition, topology means it's a classification of objects up to smooth deformation. So here, the object is this tensor network wave function, and here the deformation is the deformation of the tensor network wave function respecting the symmetry. And this tensor network wave functions is known to be numerically very friendly, in particularly in low dimensions, 1 and 2 spatial dimensions. So combining with this tensor-based numerical algorithm, this method can be used to efficiently simulate topological phases in practical models. So those are the main results. But so what I plan to do in this talk and tomorrow's talk is to try to give you these 3 applications of this machinery, and I will hopefully you see how this machinery works. So the first application is the classification simulation of competing spin liquid in a particular model. It's a so-called spin-half-Heisenberg model on the Hagen lattice. And this turned out to be an interesting model in the context of frustrated magnets. This is a pretty practical application. And the second topic would be about this classification of bosonic cohomological SPT phases. So previously, this question about the bosonic SPT phases was studied, particularly for the on-site symmetry and also for the lattice symmetry case by case. So for on-site symmetry, there's a systematic understanding by Zhong Cheng and collaborators. So here, using this machinery, this tensor network-based machinery, we obtain the following result. The main new result is the following. So you can, so in D spatial D dimension, there's a partial classification of bosonic SPT phases that are labeled by this object, this so-called group cohomology. And here, the symmetric group is SG, and the U1 is the coefficient in this cohomology group. So at this moment, you don't have to pay attention to what it means, but maybe I can explain later. The main new result is that this symmetric group can be taken as a full symmetric group, including everything, including onside and the lattice and everything. But you have to pay attention in the following sense. Because when you define this group homology, you have to define how the symmetry act on the U1 phase. It turned out that both time reversal and mirror symmetry, and generally all these determinant equal -1 spatial symmetries should be treated as anti-unitary when you compute this group homology. And for every class in this partial classification, we can construct a linear network with a function if SG is discrete. That's the second topic. Okay, so the third topic is a byproduct. The byproduct is a general connection between rather conventional SET phases and SPT phases in two spatial dimensions. So let me give you an example of what I mean. So SET, as I mentioned, it has to have a topological order, but also in the presence of some symmetry. So here, let's consider a particular SET phase. So you have topological order labeled, characterized by the Taurus code, which Joshua mentioned, and in the presence of isosymmetry. So let's say the isosymmetry has the symmetry group is identity and this Ising element G. So let's assume this G acting on this E particle in the Taurus code, square equal -1. So what this really means is this E particle, the Taurus code has this identity EM and EM, which is fermion. And so this means that this E particle carries fractional charge under the Ising symmetry. For the integer charge of Ising symmetry, the square is always +1. Itself can be +1, -1, but the square is always +1. But here, the square is -1. So that's this is basically analogous to this 1/3 charge in this lattice state. Okay. So E has symmetry fermentization, but M has trivial symmetry fermentization, namely the M square G, the Ising symmetry acting on M square equal +1. Okay, so this is actually a rather conventional SET phase. So actually one can realize this phase in some rather simple models like quantum theorem models. So the claim is, starting from this SET phase, if you condense, you can condense the M particle, which is the gauge flux of the Z2, this Taurus code topological order. You can condense this M. If you condense this M, you will destroy the topological order. You will go to some phase with trivial topology. There's no anion. But the claim is you can condense two different kinds of M particle. If you condense the M particle, carry Ising quantum number trivial, you get a trivial paramagnet, trivial Ising paramagnet. But if you condense the M, carry Ising quantum number -1, Ising all, then you will reach this non-trivial SPT. This is the Ising SPT that Zheng also mentioned. So you start from the same SET. This is a rather conventional SET. There's no gravity steady states, but you can confine the topological order in two different ways, and you can get two different phases. And one of them is SPT. How do I condense that? Yeah, so you can tune some parameters.
What are parameters in Hamiltonian?
Well, I'm not paying attention to a specific form of Hamiltonian. This is some universal result, right? So what you should visualize is you say you have some Hamiltonian supporting this SET phase, and then you can say compute the excitation spectrum So there's an m particle, which is gap, and you want to tune the Hamiltonian such that the gap of this m particle is lower. Okay? And at some point it will touch zero. When it touches zero, it's condense. Okay?
Just adding some new terms into it.
Yeah, that's right. This is very generic. So this is basically like this basically tells you that okay, maybe this side is a really conventional. This is the usual confinement deconfinement phase transition. You start from a deconfined phase to confined phase. Okay? So this is well known. But the claim is if you have symmetry, this confinement deconfinement phase transition need to be careful. And if you condense the gauge flux carries some quantum number, you can get SP. Okay. So maybe let me ask, are there more questions? And if no, I will try to move forward. Okay, so this was just one slide introduction about tensor network. I think people saw this many times. So think about the paths on a square lattice. I replace every side by this tensor. And I contract all these tensors to get a physical wave function. So here I want to mainly mention one thing. So usually people think about this local tensor really like a tensor with a lot of indices. And this I is the physical index. For example, if you have a spin system, this I can run from 1 to 2, or up down. There is a 2 physical spin, like the spin half system. And this alpha, beta, gamma, delta, they run from say 1 to D. So those are the virtual down dimension. So all I want to say is instead of thinking about this as a tensor, think about this as a single quantum state. So that's somehow more physical way to think about it. The price to pay is you enlarge your Hilbert space. You not only have physical Hilbert space, you also have the enlarge the virtual Hilbert space. The alpha, beta, gamma, delta are all states in this enlarged Hilbert space. And you put all these things together, and then you realize instead of thinking about it as tensor, you can think about it as a single quantum state, but in an enlarged Hilbert space. So why tensor network? So tensor network turned out to be very convenient for the topological phases. So in fact, in the past, the first deep insight for SPD phases was obtained by studying this MPS, matrix product states.
Sorry, how did you want to enlarge the Hilbert space? How did you want to enlarge the Hilbert space?
Yeah, because originally you only have the physical Hilbert space, but now you also have this virtual Hilbert space.
How did you want to measure this? Sorry, I may not get it. How did you measure this virtual Hilbert space?
Because somehow, you can either think about it as a tensor include, say, a lot of complex numbers, or you can think about it as a single quantum state. For some reason, which will be clear in a moment, this way is, I think, is a better way. It's a more physical way.
Also, I'm lost here too. So you have this product of A and B.
Right.
Yeah. So how do you understand this in terms of this new interpretation?
Okay. So yeah. So then you will have to. So what happens is this. So you have one virtual state, say T1 here, this one tensor here, another state here. So you make a tensor product.
Yeah.
At this moment, there's no entanglement, but somehow you introduce a new state. This is a maximum entangled state between these two legs. Let me call it the D1, 2. So this is like say this is the one right one left 2. So this is like right one equal left 2, summing over. Yeah. So it's like this. So what you do is you take this and then you somehow project this state to this D1. That's probably what's going on.
That's what I guessed.
Yeah.
But it's not really done.
Yeah. So that's because somehow you not you lose this. Yeah. Okay. So also it has a powerful numerical algorithm. But for me, the true reason why this is useful is that it's very convenient to understand how symmetry acts on global wave function in the local fashion. It turned out that all these symmetric topological phases are related to how global symmetry acts on the local patch of a wave function. So I will explain what I mean. So for example, symmetry factorization is really a question about if I create an anion here, if I have a localized symmetry action, how that localized symmetry action transforms this anion. And this local symmetry property of a global wave function is usually difficult to formulate. But in this tensor formulation, it's directly there. Because this is really like a Lego game. You put all these pieces together. So if you want to know how global symmetry transform the wave function, all you have to do is to understand how the wave function, how the local wave function, this local piece, how this guy transforms under symmetry. If you know this, you know everything, right? And you also know how any finite patch, how they transform under symmetry. So it's very convenient to understand how symmetry is realized in the local wave function, local patch. So that's very important to understand symmetric topological phases. Okay, so now let me try to explain how I implement symmetry in a tensor network. The basic assumption is very simple. It's a
sorry. So in a field theory description, can we have something like this? I mean, we have global symmetry, but we have local symmetry.
It's sort of implicitly there, but usually, I don't know. Field theory to me is somewhat formal. So you think about this. Think about maybe transcendence theory, and you can say Lafayette state, and you can ask yourself, what are the quantum charge carried by the party Hall or party particle. So those are some lesser charge. But then you ask yourself, what exactly does that mean? That actually means some local symmetry action. So you have to define how a single anion transforms under symmetry. So that's some local question.
Sorry, I'm a pure mathematician, so maybe my answer is stupid or naive. So for my point of view, local symmetry is very important in network, more important than global symmetry. Maybe how about your point of view?
Sorry, I didn't get that.
No, I say, for my point of view, I say local is more important than global symmetry in network or tensor network. How about your point of view? You think local is more important or global is more important? My question maybe is too naive for you.
No, there's no naive question.
Okay, thank you.
Very good question. So to me, I think they are probably the same. So if in this language they are sort of the same.
Because same is much major zero thing, but it's not something larger than something.
It's like if you try to implement global symmetry, you better know how this local guy transforms.
So you think global symmetry can reduce to local symmetry?
That's right.
Oh, I don't think so.
Yeah, so we will see.
Yes, use your point of view. Thank you.
Yeah, so let me try to implement global symmetry. So basically, there's an assumption, of course. The assumption is symmetry on the physical wave function is the same as some gauge transformation on the internal legs, the virtual legs. So it turned out that this tensor network construction of wave function contains a lot of gauge redundancy. So by gauge redundancy, I mean, for example, like this. So think about I contracted two tensors. It's perfectly fine that I redefine my A tensor by multiplying some matrix B, but multiplying some B inverse on the other side. So after I do this, these two local tensors, they will look differently, generally. They may look differently. But the physical wave functions are not changed. They're completely the same. So this kind of transformation, this redundancy is the redundancy in your language. So basically for every internal bond, there's a GL DC gauge redundancy. So the V can be any